EMF induced by a time-changing flux. So we've talked about magnetic flux already, but the real point of magnetic flux is that if you have a magnetic flux through a loop that changes, you will induce an EMF in that loop. And that's a strange concept, so I'm going to repeat it. If you have a magnetic flux through a loop that changes, you will induce an EMF in the loop. So let's think about that. How can we change the magnetic flux through a loop? We're going to think about three categories, three ways to do that. One, you can move the loop in and out of a field. If I have a magnetic field and I move the loop from being in the field to out of the field, then the amount of flux is going to change. That's one way of changing the flux through a loop. Another way is to rotate the loop. If you rotate the loop, well, if it's flat to begin with, you have a large magnetic flux, but if I begin to rotate it, the magnetic flux will decrease until it reaches zero. If I keep spinning it, it goes from zero to being a larger number. Okay, so that's another way to change the magnetic flux through a loop. And the third way is to change the magnetic field, to keep the loop where it is, not change anything about the loop, but to alter the magnetic field going through the loop. If I increase the magnetic field, I get more field going through the loop, and the magnetic flux increases. So the magnetic flux has changed. Also, I could decrease this magnitude of the magnetic field, and if I do that, the magnetic flux would decrease. Okay. So, I've already mentioned it, but let's put it in better language. Faraday's law. Faraday's law says that the rate of change in the magnetic flux through a loop is proportional to the EMF induced in the loop. So that's the verbal statement of Faraday's law. The mathematical statement of Faraday's law is that the EMF is equal to minus n, we'll define that in a moment, minus n times delta phi divided by delta t. So in this case, the EMF is the EMF induced in the loop. N is the number of turns of wire, number of loops of wire in the loop. Delta phi is the change in the magnetic flux, and delta t is the time that it takes for the magnetic flux to change that amount. Okay. So let's apply this. Let's say we have a coil of wire, and that coil or loop of wire has an area of 0.010 meters squared, and there's 50 turns of wire in that loop. And that wire rotates in a field of 0.25 Tesla. Let's say it takes 1 second, 1 whole second, 1.0 seconds, to complete a move from theta equals 0 degrees to theta equals 30 degrees. And I want to know what the EMF is that's induced in that loop. So we go to our EMF equation, to Faraday's law. We know n is equal to 50. We know the magnetic field. We know the area. And we know both angles. We also know the time that it takes. Now, delta phi. Another way we can write delta phi, the change in the magnetic flux, is that it's the final flux minus the initial flux. And we can calculate each of those. We can calculate the final flux and the initial flux. So that's going to be our method of attack in this problem. Now let's think of a slightly different example. Let's say we keep the loop so that theta is equal to 0 degrees. But now we're going to change the magnetic field strength so that it starts out at 0.25 Tesla, but then that magnetic field decreases to 0 in 1 second. Let's see if we can calculate what the EMF is. And so we go back to Faraday's law. We use that. We have all the information we need. It's just the numbers come out a little bit differently.